Hello and welcome to this presentation by Alberdingk. My name is Markus Dimmers and I'm going to tell you a little bit about our polymers for paper food packaging applications. Innovative barrier solutions against water, moisture and fat. In this presentation today we will have a look at the products that we are offering into this market, the polymer design of these products, some test results on paper, effect of mechanical stress on the barrier. We will have a look into oxygen barrier on PVOH paper, and finally we'll have a short summary on the different products. Starting with the product overview, we start with Alberdingk AC 4605. This is a single phase acrylic dispersion, and I will explain that later in the presentation a bit more in detail. It's in compliance with most food contact regulations, so German, European, American, Swiss ordinance, as well as the Chinese GB norm. It's used for paper, but it can also be used for foils. In case of paper, we see that as an alternative to PFAS. It comes with a relatively high solids content of 50%, neutral pH, relatively low viscosity, and very important for paper coatings with a low MFFT of approximately 5 degrees centigrade. Then we move to the next product. This is, let's say, a sister product of the AC 4605. This is the renewable version of the 4605. It's called REN AC 5605. Again, a single phase product. It still complies with all the food contact norms that I've mentioned before, but this product comes with 21% renewable resource content, which you can prove by C14 analysis. Why is it only 21%? The reason is that if you want to stick to all the regulations which we've mentioned, you need to make sure that you use compliant raw materials, and that somehow limits the use of bio-based product for the moment. The next product is different. It's called Alberdingk PC 4007. This is a ready-to-use material for paper coatings that offers excellent COBB and kit values, as well as reasonably good MVTR. This product has a slightly more limited compliance, so it's in compliance with BFR 1436. It's got the EU Plastics Directive compliance with some restrictions, the FDA 176-180 Swiss ordinance, and not the GB norm in this case. This is mainly used as an example for primers used in food packaging. It's a slightly lower solids than the products that we have seen before, 44%, and this is made of a multi-phase acrylic. And then we come to the last product for today's presentation. It's the Alberdingk PC 4750. This is again a ready-to-use product, which is mainly aimed for top coats or single layer coatings with superior MVTR performance. This product complies with BFR 14 and 36, the EU Plastics Directive, the FDA norm, and the Swiss ordinance. This is also in compliance with fatty food contact, which is also a very important thing, and that can be used for any sorts of food packaging where you need superior hydrophobicity. So instead of using PVDC, you can use PC 4750, and you should get very similar or sometimes even better performance than using halogen containing polymers. The solids content is with 45%, relatively high, again low viscosity, neutral pH. And now we will look more into the details of the polymer design. So I've mentioned before single phase products and multi-phase products, and before we go into that, we have to think about the challenges that paper as a substrate represents for us. and that is mainly the film formation. When we started looking into paper coatings, we had to anticipate the very quick film formation caused by the porous substrate, and how important it is to make products which guarantee a perfect film formation under those conditions. And how do we test it? You see here on the right hand side this picture. We apply 6 microns wet, then we apply a second layer, and then we check with a black wiping stain the quality of film formation. And in case of the top of the picture, you see the fractures in the film caused by the poor film formation. So the black wiping stain is able to color the paper. And then on the bottom, you see that when you apply the second layer, this disappears. But that doesn't mean that you'll have, let's say, a positive outcome. The fractures underneath will still, let's say, influence the MVTR and water resistance properties. So you will not want to use such kind of a layer setup simply because you've got a weak layer underneath. So that would not result in a satisfactory outcome. So in this slide, I'm going to explain to you the difference in between single-phase polymers and multi-phase polymers. On the left-hand side, you see the single-phase polymers, where you need basically one reactor and a monomer blend tank, which then continuously feeds the monomer blend into the reactor. And then you are getting particles. And these particles are all made from the same monomer blend, so homogeneous particles, as we would call them. On the other hand, you have these multi-phase polymers, where you've got the reactor again here in the center, and then you've got 2 different monomer blends. Usually it could be one is a harder, higher TG blend, and one is a softer, lower TG blend. But there could also be other differences, and these are being fed into the reactor one after the other, or in other strategies of feeding. And as a result, you are getting heterogeneous particles like those here, which are characterized like a core shell. So you've got a yellow shell and a green core, or the other way around, depending on how you feed and some other physical parameters. You can also get products that look like raspberries or half-moon structures, and that is the morphology that we are obtaining with products like PC4007. So more complex, resulting in usually better blocking resistance and other improved physical parameters. If we now look into what we would call superhydrophobic barriers, by using controlled morphology design, we look at the strategy that is being used for the PC4750. So this is a very, very particular morphology that we are trying to obtain here, and we call that the salami morphology. And that, you have to imagine, is because when you would be able to cut a particle in half and you would look at it from the side, it would look like a very fine Italian salami, where, let's say, the soft polymer, let's say the green material is the soft monomer blend, and the yellow one represents hard polymer particle. In one dispersion particle, you're getting a super fine structure of hard segment. And then when you think about it, these particles, when they smash together upon film formation, the soft material, so the low TG material, will flow off, and the hard segments, they will literally swim on top of these molten low TG material, which is represented by the green color. the individual domain size here is approximately 10 times smaller than in a conventional polymer. So as a result, when you apply the same film thickness of this polymer compared to a standard polymer, you're getting 10 folds more layers of these hard segments, which then ultimately leads to, let's say, a much more perfect film formation and a much longer diffusion way for water and water vapor. So that gives us these extremely good MVTR properties that we are going to look more into detail in the coming slides. So here you can see what I've tried to explain in atomic force microscopy. On the left-hand side, you have a standard core shell acrylic where the dark color represents the low TG polymer material and the lighter color represents the hard phase. And you can see the size of the hard phase here pretty well, so it looks like real proper spheres. That's why it's a real core shell acrylic. And on the right-hand side, you see the super hydrophobic product with controlled morphology. And in this case, as I said, the overall structure is 10-fold smaller, resulting in these superior quality of film formation. We can also prove that if we look at the contact angle of the PC4750, you can see here that we are able to reach a contact angle of 107 or 108 degrees on paper. So that shows you how good and how hydrophobic the material actually is in such a low film thickness. Here we are talking about a 6 microns drawdown. If we now look at the substrate paper, which is not as easy as one would think, what kind of paper did we use to test? So initially when we started the work, we really had a hard time because there is no standard paper, as you probably all know. So you have to find, let's say, a representative substrate which gives you a chance to show the difference in between your products, but which is also something that you can repurchase and where you have, let's say, a consistent quality. So when we started working on these coatings a couple of years ago, we found a copy paper with a very low weight of 60 grams per square meter, which was able to give us quite good differentiation. Just recently, we found another substrate which we're using now for testing, and that's the UPM Solite Lucent paper with 78 grams per square meter, because that is a paper which is designed for barrier coatings. So that shows you the full potential of the products and is probably less for differentiation, but to show what is possible using barriers on a proper substrate. So now let's get into the details of testing. Let's have a look at the start on water resistance, so COBB resistance according to TAPI 441. Just to remind everybody, how is it done? You've got a COBB tester here. You use that in different duration. So you put the paper into it, you've got water in the bucket underneath, you flip it over, and then the water will sit on top of the paper for a certain number of minutes, and that's given in minutes. So a COBB 300 is 6 minutes, a COBB 1800 is half an hour, and then later on you dry the excess of water, you dry it off, and then you weigh the paper and you check the water absorption. So here you can see already that we choose to use a COBB 1800, so half an hour of testing, and all these tests were done on the copy paper, so that is important to understand for comparative reasons. On the left hand side you can see a market standard resin that we found with a COBB of 8.6, and you can see that The Alberdingk products that are offered in this market space are always better than the market standard and at a very, very low level, so around 5 grams per square meter, which is a very, very good result for a COBB test. Then we come to the resistance against fat. That is done by the so-called KIT test, that is the TAPI 559. And we have to say that this test was invented for PFAS many, many years ago. So you could argue whether that is still the right test for a real coating. Yeah, but it's still a widely accepted testing, and again, it's done on the copy paper. Here you've got an example for a kit of 5 and an example of kit of 12, so there should be no discoloration of the paper when you apply the test solution. And if we now compare the products, you can see that all products that we are trying to explain in this video are reaching the highest kit level of 12, and the market standard is also doing pretty well at kit 11. Then we're getting to one of the most important parameters for true barrier coatings, and that's the MVTR. The MVTR in our case is measured in cups according to DIN 53122/1. It's a wet cup method. So here you can see the moisture vapor transmission rate and 23 degrees centigrade and 85% relative humidity after 1 day. And you've noticed I've had to switch off my video because otherwise you will not be able to see all test results. So the paper on its own is a very poor barrier, as you can see, with 651 gram per square meter per day. The market standard, the AC 4605 and the REN AC 5605, they perform pretty similar. And on the right hand side, you see the PC 4750 outperforming everything with 27 grams per square meter per day on the very poor substrate copy paper with 60 grams per square meter. So that's a very, very good result. And now we will go to harsher conditions. So here we do the tropical test, MVTR at 38 degrees centigrade and 90% relative humidity after 1 day. And again, we do that on the copy paper with 60 grams per square meter. And now you can see that the paper was not tested anymore, because then the numbers will go sky high. The market standard now performs at 1350. The 2 single-phase acrylics that we provide are around 1000 grams per square meter per day. And the PC 4750 is still very, very low at 60 grams per square meter per day. And I once again stress, it's just done on copy paper. Since paper which is coated has to be wound up on a roll, we also test blocking resistance. That is according to an internal method. So blocking resistance here is tested 6 microns wet. You test varnish versus paper, which makes sense because you roll up on a roll, and the face of the varnish will stick to the paper. The blocking conditions are 24 hours at 70 degrees centigrade at 50% humidity, and after that you block it for 24 hours at 23 degrees and 50% relative humidity, and you apply a weight of 10 kilograms per 225 square centimeters. And the lower the column, the better is the blocking resistance. So the market standard here for the first time outperforms the other products. AC 4605 and REN AC 5605 are single phase products, so there is no real surprise that they are a little bit more tacky, so to say, than more complex polymers. but the PC4750 still performs pretty well in comparison to the market standard and has no issues whatsoever with blocking. Another important question then, if we think about making packagings, is can you seal these products? What is the seal strength? And here we are measuring the seal strength on the copy paper. So it's probably not the best substrate to do it because it's a very, very lightweight paper. We are also using a slightly not ideal equipment. We have a Brugger heat seal machine, which is traditionally used for foil heat seal testing, so paper might not be the ideal material in this machine, and we are sealing varnish versus paper. But if you see the comment on the right hand side, you see that in all cases we get paper tear out, so it's not that the seal bond is breaking, it's actually the paper which is failing. And all products have, let's say, similar heat seal performance, all Alberdingk products I should say, whereas the market standard at the two different temperatures performs very, very differently. At low temperature you have nearly no seal force, but then at the higher temperature you get a pretty high seal force. But we are working on trying to find better equipment and try to produce more representative data. But nevertheless, all these products can be sealed without issues. Then some further testing regarding barrier properties. One particular test is the palm oil resistance, according to DIN 53116. That's basically done with a colored palm oil. And then you rate these coatings into different classes. So class 5 is the lowest class, where you only withstand 10 minutes. But you can also have class 1, more than 24 hours with a weight of more than 1 kilo on the coating. And here we'll give you some examples on how this could look like. So you apply it to the front of the paper, so the coated part. Then you inspect the backside after testing. So here you see there is some bleeding through. And then the most important thing, there is a paper underneath the test setup, which is the indicator paper, and that should also not show any stains of colored palm oil. This is an example for a 2-layer coating. So you see that the front still very, very pink. The back side has no indication, and the paper below again has no indication. So how do the products actually compare? Here we use the copy paper as a substrate and a slightly thicker film thickness, so 8 microns in this case. And you can see that only the 4605 is slightly weaker with class 3, but all other products are actually in class 2. To carry on with resistance to oils and fat, we also make oil COBB. And in case of the oil COBB, we are using castor oil, and again the test is done on copy paper. 8 microns wet application. You can see that the market standard and the AC 4605 and the REN AC 5605, they all have been tested for 2 hours, and the results are, I would say, pretty good. If you look at the PC4750, we were testing it for 24 hours, and it still, after 24 hours, outperforms the 3 others. So with 4.2 grams per square meter absorption, that's literally nothing, which again shows that the product is not just hydrophobic, but it's also lipophobic. Then automatically you will ask yourself, okay, these barriers, they seem to be almost too good to be true. How do they behave when you fold the paper or you freeze the paper? So what happens if there is mechanical stress? And now we will just focus on the PC4750 because that's let's say, the ultimate barrier product. Here we look at COBB 1800 values, so half an hour water resistance on the copy paper. So on the left hand side we see the PC 4750 without mechanical stress around 5. Then if you fold the film, nothing really changes, so it remains as it was before, which indicates that the flexibility of the product is sufficient. And then if you freeze the film for 24 hours at -20 degrees, it goes slightly up to 6.8, but that's still, let's say, a marginal difference and no real harm done to the barrier layer. If we then go and look at MVTR, and in this case we will again focus on tropical conditions because that's the most harsh test that you can think of. On the left hand side you've got the comparative data of PC4750 on copy paper without any mechanical stress. It's around 70 MVTR. Then if you fold it, you see that there is an increase in the moisture vapor transmission, which might be due to some micro cracking. And then when you freeze the film, it actually seems to improve a little bit, but it might also be related to the margin of error in the method, where we go down to 52. So these tests show that mechanical stress is not a big issue for the quality of the barrier because the product offers enough flexibility to withstand this. Then if we think further, what happens if you try to compare these water-based non-halogenated materials to a well-renowned brand like Diofan, so PVDC-based polymers, because we all know that people would like to move away from halogens, not just PFAS, but maybe also away from PVDC. So here we are comparing the PC4750 in green versus a Diofan 585, which is being recommended for paper barrier. And we are testing here the MVTR at tropical conditions, so 38 degrees centigrade, 90% relative humidity. And we've changed the substrate, pay attention. In this case, we are using the UPM solid lucent paper with 78 grams per square meter. And the result speaks for itself. You can see that the PC4750 now, when it's used on a proper substrate, we are able to achieve as low values as 14 for the MVTR, where the Diofan is at 33 roughly. So meaning that our non-halogenated polymer outperforms the Diofan by far, and gives you also an idea about the possibilities using these kind of polymers in packaging applications. As we have been looking at the results on the solid lucent paper now, let's have a look at a substrate comparison. So if we compare the copy paper that you've seen before in all the testing versus the solid lucent paper, and we just look at the MVTR at tropical conditions, you see that on the copy paper we are ranging at roughly 70 grams per square meter per day, but changing to the proper substrate we are able to go down to 14, which as I said before stresses the importance of the right paper for the individual application. Another important factor in barriers is barriers against oxygen, and as you probably know, acrylics are not really offering inherent barriers against oxygen, so you have to find other ways to make these barriers. And in this case we will look at a PVOH coated paper which has a very good oxygen barrier, and we measure that using an Oxtran machine. But the PVOH is a very hydrophilic polymer, and you need to probably protect it against other things to make sure that you have your oxygen barrier, but you're also able to offer a barrier against anything that's water-based. So here in this chart, we look at the O2 barrier at 23 degrees centigrade, and we see that the PVOH coated paper on its own is at 285. If you then coat it with a two-layer system made from PC4007, followed by a top coat made with PC4750, you see that the oxygen barrier is not affected by the coating. So 285 or 294, that is literally the same result. But then if you go and check the MVTR properties under tropical conditions, you see that the paper with the PVOH on its own has no MVTR barrier. So you have 2000 grams per square meter per day. That does not provide any protection whatsoever. If you then just coat these PVOH coated paper with 6 microns of PC4750, you are able to bring it down to 850, which is again not bad, but comparing the results that we've seen in the slides before, a little bit disappointing. Then if you choose to coat it with a two-layer system, first starting with PC4007 as primer, followed by the top coat with 4750, you bring it down to 110. So that's where proper MVTR starts, and then you can make it even a little bit better if you use some fin talc in the PC4007 primer and then recoat it with a 4750. That is where the talc gives you additional barrier properties thanks to its lamellar structure. Then we also need to check the COBB resistance. In this case, we cannot compare to uncoated paper because that was simply not measurable. That shows you how weak the water resistance actually is. And the paper with the PVOH and the PC4750 in a COBB 300, we are getting to 48 grams per square meter, so that's actually quite high for the short period of time. But then again, if we use a two-layer system, we'll bring it down to 8. So we are able to make a coating on the PVOH which does not destroy the O2 barrier, but which gives you additional protection against water and moisture. So here I'm back. Coming to the summary of our presentation. As you probably have realized, we have many products for paper packaging, and I've not been showing you even the whole product range. We can do renewable resource-based products already in commercial scale, the REN AC 5605. But it's for sure that if you want to have full food contact compliance, it is required to use other techniques to increase the renewable share. That's why we are working on an ISCC Plus mass balance approval for our factories, so that we are able to offer mass balance approach versions of the products in question, since that will not affect the food contact compliance. We've also seen that PC4750 is a potential replacement for PVDC polymers. That means you can make true halogen-free barrier solutions, which are even outperforming the PVDC polymer. You can make very high MVTR barriers without losing water or even fat resistance. If you think about the contradiction that if you make something that is very, very hydrophobic, usually you would expect it also to be lipophilic. In our case, that's a very, very good compromise that we've been able to make. And finally, we recognize that oxygen barrier is becoming more and more important. We need to make further tests, and we probably rely more customer substrates to do additional testing, but it seems that we are able to guarantee or to provide an improvement in water and moisture vapor transmission rate without harming the oxygen barrier coating solution that customers would like to use. And if you've not found what you've probably been looking for, just talk to us. We are doing lots of testing. We keep developing new products every time. And we would be really, really happy to get in touch with you and to exchange more information or to do testing on your own substrate to show you what Alberdingk products can bring to your paper substrate. Thank you very much and have a great day.